On a frictionless horizontal track, a glider oscillates at the end of an ideal spring with a force constant of 2.5 newtons per meter. The graph below shows the acceleration versus time, and we are looking for the mass and the maximum displacement of the glider. Alright, so kind of given that information and knowing that we have an acceleration versus time graph, if we look over here, we know that the acceleration should be the greatest on the ends over here where the velocity is 0 and the spring is fully stretched. So we know the acceleration as it is at a maximum value on the end. Now, for argument's sake, since we know the acceleration is going to be at a maximum value, and if my x is equal to 0, positive is to the right, negative is to the left. At one of these points here where you have a positive acceleration, right, the spring force will be exerted in the positive direction here, which means the acceleration will be a maximum value at negative a. So we can look at this, all right, if we call this negative a, it's going to start over here at negative a, it's going to go through one oscillation. This on the graph would be positive a. That's amplitude, all right, with a negative acceleration, and then over here, again, would be at the negative amplitude location. All right, so for one whole cycle, we're going to go from time 0.15 seconds to time 3.5 seconds, or 0.35 seconds. That being said, we know we can then say the period of this is 2.5 seconds. You guys are probably wondering, well, why is that important? All right, besides for, giving us the spring constant K in the problem, okay, they're asking for the mass. And as we've been talking about all week, we know that the relationship between the period, the mass, and the spring constant is T is equal to 2 pi radical m over K. So now that we have the period, and we know the spring constant in the problem, we can solve this expression for the mass and determine what the mass of the glider is. So if we square both sides, we're going to get T squared is equal to 4 pi squared times m over K. And then to solve for m, we'll get T squared times K divided by 4 pi squared is equal to the mass. Here we get the mass of the glider to be 0.0025 kilograms. As I was saying, the mass of the glider is 0.0025 kilograms. All right, now they're looking for the maximum displacement from the glider from the equilibrium point. So if we know the mass of the glider is 0.0025 kilograms, and we're looking for the maximum displacement from the equilibrium point, the graph actually gives us the magnitude of the acceleration. So we know the magnitude of the acceleration is 12 meters per second okay, and I'm taking either from when it's at negative a or at positive a. We just know the magnitude of this is 12 meters per second. Depending on what location, we'll look at that then. All right, so to figure that out, we know at either positive a or negative a, it's going to be the spring force divided by the mass is equal to the acceleration, where the spring force is equal to K times delta x over m is equal to a. Well, they want to know what the maximum displacement is, delta x. So at either the maximum acceleration in one direction or the other direction, at a, essentially, capital A that is, this can change into K times A is equal to M times little a. So then the maximum displacement will be M times A divided by K. Substituting those numbers in, we get an amplitude of 0.012 meters, or 1.2 centimeters. All right, to determine the spring force, you can do this a number of ways at this point. You could say that this is M times A, or K times capital A. Either way you do this, it will ultimately equal about 0.03 newtons. Now, write an expression for the position as a function of time. So we know the amplitude. So position is going to be A cosine omega t. All right. We know the amplitude in this case is 0.012 meters times cosine of 2 pi over the period, which is 0.2, times the time, which is t.